Alrighty, so linear kinematics, velocity. Now, we all know that cheetahs travel very fast, right?
No, it's fast.
No? You don't need to know that for the test, but cheetahs travel fast. Alright, so what is distance? Do you really need to write this down?
How far something moves?
How far something moves with no regard for direction. In other words, if we go out and walk around the track 4 times, 1,600 meters, 1 mile, that would be the distance traveled. Right? That would be the distance traveled. What a nice surprise that was. And I had something to talk about. And the rate of motion is called speed. So if you could walk the track, say in, how long do you think it would take you to walk the track?
I don't know.
Like in the good old days when I was a little bit more athletic, I could run it in about 60 seconds. But I'm not going to do that today.
Actually?
Yeah, oh
Yeah, it's actually not bad.
yeah.
It's not that impressive, never mind.
No? Sorry, man. I think my best time was 52. If I'm going to go out and walk it, what would it take me? Maybe 3 or 4 minutes, probably something like that, right? So that would be my speed, right? I guess it wouldn't be the time. That would be my time. If it was 400 meters, right? I guess if I'm walking the 400 meters, let's say 4 minutes, because then I can do the math in my head. 4 minutes, oh no, I can't. I guess that would be 100 meters per minute, wouldn't it? Right? Did we measure speed in meters per minute? Good, but in 4 minutes there would be 60 seconds. So it would really be 400 divided by...
In 1 minute would be 60 seconds, not 4 minutes.
Yeah, well, but in 4 would be 4 times 60, right? So that would be 240, wouldn't it? Right? So what's 400 divided by 240? It's going to be about 1 point something or other.
Yeah. 1.6.
1.6? Okay. So I'd be walking about 1.6 meters per second. That seems about right, doesn't it? About 1.5 meters, about there, per second. That's actually kind of slow, I think, isn't it? That'd be like strolling. Okay, so anyways, here's another example on a bike traveling 6 meters in 1 second, 12 meters in 2 seconds. The speed is 6 meters per second.
So how long will it take you to walk the track?
Right, like today?
No, like any day.
I don't know, I've never tried it.
Oh, okay, cool.
Ask me after lunch. Or ask me tomorrow. I'll time it. I'll figure out my speed. Come and join me. Get another sticker.
Oh, yeah.
Okay, so what's displacement? Displacement is, Mr. Jack should have that up there on the screen for me. The change in position in a particular direction is always a straight line segment from one point to another, right? Translated, it's how far you went and in what direction. Or really, it's, this is what you really need to write down. How far away from start. That's really what it is. How far away from start are you? Alright, so what's displacement is how far away you are from where you started. So in other words, if I do walk the track 4 times at lunch, as JC pointed out, my displacement is going to be 0 because I'm going to end up exactly where I started. If I do. And delta D is final minus initial. We learned that in the vector unit. Displacements are vector quantities, can be combined in a vector fashion, which means tip or tail or whatnot, right? So velocity is speed in a particular direction, making velocity a vector quantity. And we saw that when we did the vector unit as well, right? Velocity is speed in a particular direction, right? You might have a bullet train like that one there, traveling at a pretty high velocity, right?
What would the graph look like for walking?
Okay, now a position time graph, like Sean and I were just talking about, a position time graph will also show the speed or the velocity. Thank you. Position time graph will also show the speed or the velocity. Now there's the graph that you have, right? You have that graph, right? So this particular graph, if you want to call it graph A, if you just want to take your sheet and just put in your notes, C graph A, and just label that as graph A, that's another way to do it too. This graph shows 3 objects moving at a constant velocity. How can I tell they're constant? Straight lines.
Yeah.
Please note the difference between a straight line and a flat line. Different things. The velocity remains the same over the entire displacement. The result is a straight line graph. So what we're going to do now is we're going to come up with the slope for line A, line B, and line C. Now, does it matter what points I pick to find the slope? No, it does not. Okay? So I'm going to pick, I've also actually already got a little sort of triangle made in there. So what's the rise of graph A right here? It's from like, this is the rise, right? It's from 6 to 3, right? So I'm going to write 6 minus 3 is my rise, right? 6 minus 3. And then my run is from 1 to 2, or 2 minus 1.
Yeah.
Giving me a slope of 6 minus 3 is 3. 2 minus 1 is 1, giving me a slope of 3. I'm going to give you guys a couple minutes to do the slope of B and C. You should realize already, maybe not have thought of it, but if slope A is 3, B and C are going to have to be less than or greater than 3. Why less than?
Because the angle, like, because.
Are you saying because they're not as steep?
Yes.
Okay. That's what you're trying to say? Because they're not as steep.
Exactly what it was trying to
Okay. So B and C should be less than 3, right? Let's just try B here. So what's the rise on B? It goes from 2 to 4, right? So it's going to be 4 minus 2, and the run is from also 4 to 2. So that's going to be 2 over 2 or 1. Now I really should have meters per second written in here. And slope C should be, let's just see here, the rise is from 1 to 2 approximately, so we're going 2 minus 1, and the run is from 3 to 6, so that's going to be 6 minus 3. 2 minus 1 is 1, 6 minus 3 is 3.1/3, or 0.3 meters per second. And all of those are, of course, positive. Yeah, we're good?
Real good.
Okay. Now, as Nick was pointing out here, the bigger the slope value, the velocity, the steeper the line. Is that an important thing to know?
Yeah.
And I'm thinking most of you just sort of know that already, right?
Yeah.
Thinking most of you already know that. You probably don't need to write that down. The bigger the slope value or the velocity, the steeper the line. And those are all positive. Now, in that worksheet from the other day, we briefly touched on this. The average speed is found by dividing the total distance by the elapsed time, the distance by the time, right? And the average velocity is found by dividing the total displacement by the elapsed time. And oddly enough, both of them use the same formula that you've seen in grade 10. V bar equals d over t. Right? Nothing new there. What does the bar over the v mean? No. No, it doesn't mean it's a vector. It means average. You're thinking about, whoever said that about vector, when there's a little arrow over there, that it means that, right? Yeah. So in the mathematical formula, v bar equals d over t, the average velocity. And the d could stand for distance or displacement. Okay? I'm going to try to avoid using the word speed as much as I can. It can get a little confusing. If you're in doubt, assume it's velocity. I might say speed, but I might mean velocity. Okay? But you do need to know that average speed is the distance divided by time, and the average velocity is the displacement divided by time. Here's an example. Suppose you ride your bike 120 meters in 20 seconds. Your average speed would be 120 divided by 20, or 6 meters per second, right? Pretty straightforward. You saw that in grade 10, right? No big deal there. Anybody feeling the need to write any of that down? No. But if I ask you a little harder question, suppose you start at 0, ride your bike 80 meters forward, and then turn around and come back 30 meters, all in 20 seconds. What's your average velocity? Well, my starting position is 0 right here. My final position is plus 50. Do I care that I went 80 and then 30?
No.
Displacement only matters. Where'd you start? Where'd you end? I started at 0. Now, when I was doing these notes this last period, actually, I added that in. You start at 0, because I thought maybe that might be confusing. But what if it didn't say you started at 0? Can you assume you started at 0? Probably. Probably you can. If they don't explicitly say you start at 0, you can likely assume that wherever you started is 0. So would that have been confusing if it just said you ride your bike 80 meters forward and then 30 meters back? You could probably come up with a 50-meter displacement anyways, right? So I started at 0, my x is 0, my final position is plus 50. My delta d is 50 minus 0, right? Right? My displacement is plus 50. And then I plug that into my v bar equals d over t, and I get plus 2.5. That's my average velocity or speed. I started to say that as a question, then I changed my mind. Is that the average velocity or the average speed? Velocity, because I'm talking about the displacement. Okay, so the average velocity is 2.5. Really?
Beanbag.
Like, you weren't even hiding it. And you're like
mine.
approximately 1.5 meters away from me. Okay, average velocity, 2.5 meters per second. What's the difference here? I dealt with the displacement. Now, some people might think, average velocity here. What I do is I take my 80 and divide by 20, and then I take my 30 and divide by 20, and I add them together and divide by 2. Don't be one of those people. Those are the wrong people. Don't do that. Okay? Average velocity is displacement over time. Okay? Yeah? Good. Now, these have all been examples of constant velocity, right? Straight lines. Since the velocity is constant, the velocity between A and B, and we've seen this already. This is nothing new either, right? Okay? Do I have to take the total displacement? And there's a reason I'm showing you this example. I'm going to point that out in a second. You have this graph. What is the velocity between A and B? Well, it goes from 3 to 4. So there's my 4 minus 3. It goes from 4 to 6. There's my 6 minus 4. My average velocity for just that interval is 0.5. Because it's a straight line, the average velocity for the whole thing should also be 0.5. Now, here's the mistake people make. Don't make this mistake. They just do this. They go, and I almost did this when I did the notes. They just go, 6 over 10, 0.6. What's wrong with that? I went 6 from the end. 6 is the rise, and 10 is the run. 6 divided by 10, 0.6. What's wrong with that, Nick?
You gotta find the points where it's not up and then pick the rules. Y2 minus Y1.
I guess. If I'm asked to find the overall, the total velocity, total average velocity, how come I can't just take the endpoints? I'll give you again a little hint.
Because non-zero.
Yeah, it doesn't start at 0, does it? But people do that all the time, Sean. They just look at the endpoints and they divide, and they always get it wrong.
It did start at 0?
If it starts at 0, you can, because really all you're doing is you're going like, if it was starting at 0, it'd be 6 minus 0, right? So yeah, you can do it when it starts at 0. But in this case, and I specifically picked this one to show you this, right? You have to go 6 minus 1, and then 10 minus 0. Okay, do you see the difference?
Yeah.
Now, most of us know that when you go for a walk, you don't walk at a constant speed. You start off at 0 and you have to speed up, and then when you get to wherever you're going, you gotta slow down.
Sometimes trip and fall.
I think that just happens to you. So that graph right there, would that graph show me speeding up and slowing down? How can I tell it shows me speeding up, slowing down? Here I've got a little curve, and there I've got a little curve, right? This one is curving up, and this one is curving down. So it starts at 0 meters per second, kind of flat, speeding up to about 3 seconds, right about here. How can I tell it's speeding up to there? Because it's curving up to there. That's interval A. During interval B, it moves with a constant speed, straight line, slowing down during interval C. This we call variable velocity. And when I said it like that, what does that sort of imply? Variable velocity. What does the word variable mean? Like in math class, Leroy. What's a variable in math? Well, a letter, right? It stands for any number, right? The value of it can vary. So a variable velocity means, variable velocity means a velocity that can do what? Can vary or can change. Is the line straight for variable velocity? No, in fact it's curved. Curved. Curved right there. Here's another new word for you. Well, it might be, I don't know. Instantaneous velocity. Instant. What do you have at home that's instant? Instant oatmeal. It's not. It's not really instant, is it? It is. They should call it
1 minute oatmeal.
or not so long oatmeal, or kind of quick. Instantaneous velocity is the slope of the curve at a single point or instant. Now let me just go back a slide here a second. Okay, let's just go back here. The slope there is the average velocity. I'm not sure why I'm hanging on to that. Right? The slope there is the average velocity. What's the slope between A and B? 0.5. This one was wrong here, by the way, wasn't it? Right? The slope there is 0.5. The overall slope is 0.5. Is there any point along the line where it's not 0.5? Always 0.5. Okay? Okay. Now, instantaneous velocity is the slope of the curve at a single point or instant. How can you find a slope with only one point? Like slope is always rise over run, isn't it? It's always y2 minus y1. What if you don't have a y1? What if you just got a single point? What if I just got that point right there? I want to know what's the slope at one point.
You go from 0?
You can't. You can't get the slope of a single point. So to determine this, we need to find the slope of the line that is what we say tangent to the curve. Okay? Anybody know what the word tangent means? You got your sine, your cosine, you got your tangent.
Opposite over.
Yeah, opposite over adjacent is good, right? A little bit different meaning here. A tangent line is a line that just touches the curve at that single point. And the slope of the line in math terms approximates the slope of the curve. In other words, the slope of the line is the same as the slope of the curve at that little teeny tiny point. And we'll finish up there tomorrow.
Okay.
I didn't realize the bell was going.